Welcome, my name is Juliet. I am PhD student at the Center for Bioinformatics and Molecular Simulation from Talca University, and I am part of the team working with Professor Wendy Gonzalez in the structural and functional understanding of ion channels. In particular, we are working in the identification of common structural patterns in drug binding site of ion channels. This could be useful for the rational design of multi-target ligand drugs with applications to polypharmacology. In this work, we selected as targets the potassium Kv1.5 and sodium Nav1.5 cardiac ion channels. These channels are involved in cardiac antipotential and they are important targets for atrial fibrillation. These channels share a similar tetrameric fault and functional domains. Importantly, the combined inhibition of these targets is predicted to provoke a synergetic effect according to mathematical models of heart electrophysiology without alterations in ventricular. The latter is a good news since ventricular proarrhythmia is one of the unwanted side effects associated to antiarrhythmics currently used in clinic. To explore the potential similarities at the binding site of these two channels, we selected flecainide and Kv1.5 antiarrhythmic drugs as reference. Flecainide is in clinical practice for recent onset atrial fibrillation, and it mainly blocks Nav1.5 but also potassium channels, including Kv1.5. Kv1.5 advanced up to clinical 2, up to phase 2 from clinical trials. It blocks potassium Kv1.5 and also inhibits sodium Nav1.5 ion channel. Following this introduction, we will go to results. To perform binding site comparison, the knowledge or prediction of binding site is needed in the first place. For flecainide, we predicted its binding site in Kv1.5 guided by functional mutagenesis studies. We use ensemble docking and a number of frames from ND simulations as input structures of the target, and later we perform rigid docking with the ligand on each frame. In case of Nav1.5, the flecainide binding site was already known from cryo-EM structure. Here we can see our results from ensemble docking, and we can appreciate that this drug, flecainide, has a similar binding mode in Kv1.5 compared to its binding mode in Nav1.5 cryo-EM structure. The piperidine ring is pointing to the central cavity in both channels, while the trifluoromethyl inserts into the subunit interface in Kv1.5 and inserts into fenestration in the sodium channel. Then these complexes were subjected to ND simulations using Desmond and physicochemical characteristics of flecainide binding site in each frame were computed using FPocket, and also interactions were analyzed using FLIP. FPocket characteristics were used for binding site clustering, and the representative structures from clustering were compared using pocket match, and we found similarities between both binding sites. Finally, we used pocket align for the structural alignment of the binding sites. And here we will see these results regarding flecainide binding site comparison. In this picture, we can see the list of 10 pair of equivalent residues at flecainide binding site in Kv1.5 and Nav1.5 sodium channel, which are listed herein. And on the left, we have the structural alignment of these equivalent residue pairs. We can see that it is a good fit, and also RMSD values are lower than 2.5 antrons in most cases. In this image, we can see at surface level the mapping of the two common patterns consistent of two matching areas. We found a common hydrophobic patch in Kv1.5 and its equivalent in Nav1.5, which are shown in gray color, formed by aliphatic non-polar residues. And we also found a common polar region, which is shown in blue in both channels. We also identified different feature only present in Nav1.5, which is the existence of aromatic residues in this equivalent region, which is shown in green in both channels, but in case of Nav1.5 is formed mostly by aromatic residues, which also have putative stacking interactions with the ligand. We presume that these aromatic residues exclusively present in Nav1.5 could be responsible for flecainide's high affinity compared to Kv1.5. And the latter is in agreement with previous reports where the substitution of this valine residue by phenylalanine in Kv1.5 increases flecainide affinity in constant to wild type. In addition, we also predicted Kv1.18 putative binding mode in the sodium channel using as a starting point two drug binding sites from the central cavity, and we also use an ensemble docking protocol. We noticed that this drug occupies the central cavity with extensions to fenestrations and a total of 9 residues, which are listed here and shown in these pictures, are predicted to be involved in direct binding with the drug. At present, we are working on mutant construction and their evaluation by whole cell patch clamp. We obtained this mutant and we already confirmed the presence of the mutation by alanine using the DNA sequences. And well, we are working in the rest of the mutations. Well, our results give insights into the existence of a putative consensus drug binding site in Kv1.5 and Nav1.5 for flecainide. Hereafter, we are planning to complete the comparisons of Av0118 binding site in these two channels. And finally, I would like to send to Fondesit and Minicat to support our work, and also thanks for the opportunity to present our results in this Congress. I hope you like my talk, and thank you very much.